This video is about increments, differentials, and their interpretations. This will be the first video. There will probably be one more, maybe two more videos to complete this lesson. So first we're going to discuss what a differential is. So we'll define differential for you. And then once we know what a differential is, we'll compute differentials. Then we'll review a little bit by finding the tangent line approximation to a function at x equals x naught. This is also known as the linearization of y at x equals x naught. This is just computing the tangent line, but we're going to look at it differently. We're going to use the approximation, or we're going to use the tangent line as an approximation to the function. So we'll compute a tangent line and we'll look at the similarity between the y values on the function and the y values on the tangent line. And then we will discuss how the tangent line is related to our interpretation of the differential. So we'll define something called the increment of y, and we will look at the differential of y evaluated at a particular value, x equals x naught. And in those circumstances, when the differential is evaluated at this point, we can compare this delta y and the dy. And all of this is related to the tangent line approximation, which is why we're bringing that up. So those are the three main topics of this video. So let's get started. First of all, the differential is actually really simple to calculate. The differential of y is defined to be this. If y equals f of x, then the differential of y is denoted by dy, and dy is defined to be the derivative of y with respect to x, so just f prime, times dx. Sometimes people will call this the differential form of the derivative. I don't tend to do that because the derivative is actually a function. But the differential of y is that derivative function times dx. So it's actually very simple. If you can calculate the derivative of y, you can multiply it by dx and calculate the differential of y. It's really no different. So here is a very simple first example. If y equals x cubed, the differential of y is the derivative of x cubed by the power rule. That's 3 times x to the 1 less power, so 3x squared times dx. Super simple. If somebody asks you to find the differential of y, all you do is say dy equals the derivative times dx and you're done. That's it. It's very simple. So let's say somebody asks you to compute the differential of this function. Well, this is slightly more complicated, but the principle is the same. All you're going to do is take the derivative of this function and then multiply by dx. So first I might compute the derivative. Since I have a product of two functions, this polynomial function in x times this trigonometric function, I would use the product rule. So we'll take the derivative of the first function, and then we'll multiply it by the second function, undifferentiated, and then we'll add the derivative of the second function, multiplied by the first function, undifferentiated. And then we just compute those two derivatives. There you go. The derivative of x to the 4th, by the power rule, we bring the power down, multiply by x to the 1 less power, 4 minus 1 is 3, and bring that sign of 2x down. And then over here, if I want to take the derivative of this, I notice that I don't have just an x inside my trig function, I've got a 2x inside. So that means I'm going to have to use the chain rule. According to the chain rule, we take the derivative of the outside function first. Derivative of sine of a function is cosine of that function. Then you put your inside function back in, Don't take its derivative yet, just plug it back in, and then multiply by the derivative of the inside by the chain rule. And then don't forget to bring your x to the fourth down. And I see I'm done with this piece. The only thing I have left to do is this derivative. The derivative of a constant times x is just my constant. So this is y prime. I had to use the product rule and the chain rule within the product rule. Typically, we write these polynomial functions in front of trig functions, so it doesn't look like it might possibly be multiplying that angle inside the trig function. So I'll put the 2x to the fourth out front. So all I did was compute a derivative. And now if someone asks me for the differential of y, I take the derivative. Which has two terms. I've got one term here and one term here. So I need parentheses around all of that. Take that derivative and I multiply by dx. Excuse me. That's the differential of y. So it's actually really simple. All you do is take the derivative and multiply by dx. As long as you can take a derivative, you can compute a differential. Okay, now we're going to look at tangent line approximations to functions. This might seem completely unrelated to what we just did, but it's actually related to a geometric interpretation of this, as we'll discuss later. So here's the idea. So let's say I have some function, y equals f of x. Maybe it looks like this. Earlier this semester, we found the tangent line to y equals f of x at a point. So let's say you wanted the tangent line at x equals x naught. Well, in order to find that tangent line, we needed two things. We needed the slope of the function at x naught, and we needed an xy pair. Well, we've got x, it's x naught, and to find the y value that goes with it, we could just substitute into the original function. That would give us the y that goes with that x. So we'd have f of x naught as our y value and x naught as our x value. And then we use the derivative to find the slope. Remember, the derivative is a formula for the slope of the function at a point. It would give us the slope at any point as long as we were able to plug that x value into the derivative function. So maybe if I am right here, I got my Census Bureau straight edge. Here we go. Try to make it tangent to the curve. There we go. No, it does not look like a tangent line. For some reason, my pen's not lining up with it. Okay. And we were able to calculate the tangent line. Ignore the part that's not tangent. Focus on the part that is tangent to the curve. Okay. So we've already done this. We've already discussed how to find the tangent line to the function. And remember how we did that. We computed the slope. And the slope is just the derivative of our function, but it's evaluated at this particular x value. When you substitute in that x value, you're going to get a number. That's the slope of your tangent line. And then after we found the slope, or maybe before we found the slope, the order really doesn't matter here, and we needed an xy pair on that line. If somebody gives me x naught, I can find a y value that goes with that. If that line is tangent to the curve at this point, x naught and f of x naught is a point that lies on that line. So if somebody gives you x naught, you need to find the y that goes with it. So I'm going to call that y naught. Y equals f of x naught. You just substitute in x naught to your original function that's giving you the corresponding y value. And that implies that x naught y naught, which is x naught and f of x naught. I know it looks like alphabet soup, but that's just a number and that's just a number. That is a point that lies on your line. Okay, and then we said if I've got a slope and I've got a point, I can use point slope form to write the equation of the tangent line. And remember, in point slope form, y is a variable and x is a variable, so you don't want to substitute those. You're going to substitute in an x naught and y naught, and that's going to be given by x naught and f of x naught. And you're going to substitute in a slope, and that slope is the derivative evaluated at x naught. So this is the equation of your tangent line, and then usually we would solve for y by adding y naught to both sides. Okay, so we've already done this before. We've discussed this already. Say, well, what does this have to do with anything? Why is this new? Well, the new part here is that we're interpreting this differently. Here's the idea. If I'm looking at this function, looks like we've got a at least fourth degree polynomial function, right? We've got a lot of hills and valleys. But if I'm interested in the function near x equals x naught, notice that if I zoom in right here, now the function, which is given by that black curve and that red tangent line, this one, not the mistake that's right next to it, they're almost indistinguishable. And if I zoom in even further, now they're really indistinguishable. So the more we zoom in, we keep zooming in and zooming in and zooming in, the more indistinguishable the tangent line, so let's do it like this, the tangent line and that curve become. Why is this possible? It's because the function is differentiable. There's no sharp corner there. If I get closer and closer and closer, I look at this and I say, oh, look, there's a little gap. I don't want a gap. Let's zoom in again. Eventually, I'm going to get to the point where the red line, which is the tangent line, and the curve itself are indistinguishable. So we're saying the tangent line is an excellent approximation to y equals f of x as long as I stay close enough to x naught. So if I get very, very close, I might as well use the tangent line to approximate the function rather than using the original function. Say, that one's complicated. Wouldn't you rather just work with a linear approximation? Linear approximations are nice and very easy to work with. So maybe we would want a linear approximation to the function at that point, and the tangent line is providing that linear approximation. This textbook author doesn't do it, but another textbook author calls the linear, this tangent line approximation to y equals f of x at x naught, the linearization. Of y equals f of x at x equals x naught. And again, we're thinking of this differently, even though we're computing it in exactly the same way. We're just thinking of it differently in this circumstance. Whenever someone asks you for the tangent line approximation to the function at a point, or the linearization of a function at a point, they're basically saying, find the tangent line and use it to approximate the original function there. And the idea is that's a good idea because if we get closer and closer and closer, if that function's differentiable, eventually we're going to get so close that we can't tell the difference between the line and the curve anyway. So that's the idea. So let's compute a tangent line approximation for a particular function and then find the linearization of y equals f of x at x equals x naught. So let's say our function is f of x equals the square root of x plus 7, and we're interested in the linearization of the function, or you could also say find the tangent line approximation to the function. At x equals a particular value. This time it's given to us and it's x equals 2. I wonder if we can zoom out a little bit. Zoom actually won't let you zoom out. That's interesting. Okay. So f of x is this function and we're finding the tangent line approximation to the function at x equals 2. Now, in other words, they're saying find the tangent line. So we're going to go through that same process that we used before to find the tangent line. First, let's compute the slope of the tangent line. And the way we do that is we compute the derivative, and then we evaluate the derivative at that particular x value. So in this case, that's x equals 2. That's going to be the slope of the curve at that point. So if I'm going to take the derivative of this, it's helpful to rewrite it. Remember, there are implied parentheses there. It means there's an implied 1 there and an implied 2 there. So this is x plus 7 to the 1/2 power because of exponent properties. And so when I write it like this, it's very obvious. I need to use the chain rule to take the derivative. So we'll compute the derivative using the chain rule. My inside function is x plus 7. I'm taking the derivative of a function to the 1/2. The derivative of a function to the 1/2 is 1/2 of that function to the 1 less power. And 1/2 minus 1 is the same as 1/2 minus 2/2, and 1/2 minus 2/2 is negative 1/2. Then you plug the inside function back in, and you multiply by the derivative of the inside by the chain rule. Derivative of x is 1, derivative of 7 is 0. Derivative of a constant times x is just 1, or it's just that constant, which happens to be 1 in this case. And derivative of constants are 0. So this is my formula for the slope. Remember, derivative gives you the formula for the slope of the curve. Now, I still don't tend to think in terms of negative exponents, so I'm going to rewrite it using this property. Used a couple of properties here. So far we've said the nth root of x to the m is x to the m over n. And now I'm about to use this rule. X to a negative power is 1 over x to the same power but positive. So that power can be written as a positive 1/2 if I put that x plus 7 in the denominator. And if we multiply straight across, we get this. Okay, so that's f prime. Still only have the formula for the slope. I don't actually have the slope. In order to find the slope, I need to substitute in x equals 2. So the slope of our tangent line is this, and I think I'm going to change that 1/2 to a square root. So I've got that. That's 1 over 2 times the square root of 9. Square root of 9 is 3. So 1 over 2 times 3, which is 1/6. So that's the slope of my line. Now remember, you need two things. You need a slope and you need a point on the line. Well, we've got an x value on the line. We need to find the y value that goes with it. Well, remember, f of x gives you y values. So we need to find the y value that goes with that x value. So we will compute y naught, which is f of x naught, which in this case is f of 2. So say y naught is f of x equals 2. And we get the square root of 9, which is 3. And so that means the point x naught, y naught, which is 2, 3, is on our tangent line. Okay, so we've got the slope, we've got an xy pair. Now we're going to substitute into the point slope form of the equation of a line to find the tangent line. Okay, and remember what point slope form looks like. It's y equals, or y minus y naught equals m times x minus x naught. Okay, the x and y are variables, so you want to leave those alone. M is 1/6, so we sub that in. X naught is 2, and y naught is 3. So that is the equation of our tangent line. But if we're using this as an approximation to the function, usually we have to get y by itself, and then we're going to replace it with standard notation, or at least the notation being used by our textbook author to represent the tangent line approximation to this function. One way you could do this is you could distribute the negative 1/6, positive 1/6. I've got 1/6 times x is 1/6x. And then I've got 1/6 times 2 over 1, which of course is 2 over 6, which is 1/3. And then we'll add 3 to both sides. And I need a common denominator, so I'll multiply by 3 over 3. So I've got 9 over 3 minus 1 over 3, that's 8 over 3. So that's my tangent line. In slope-intercept form. Okay, now when Larson and Edwards, the authors of our textbook, ask you for the tangent line approximation, they don't usually use y equals mx plus b form like this. They solve for y, and then they replace y with t of x. I think they're using t of x to represent tangent line approximation. So they're saying this is a tangent line approximation to the function. So this is approximately equal to y equals f of x, as long as we're near the point of tangency. So as long as we're near the point x equals 2, y equals 3. Okay, in order to get a better sense of this, I think I want to draw the graph of our function, let's draw the tangent line to the function, and then we'll also come up with a table of values, and we'll show how similar the y values are in the tangent line to the y values on the function y equals f of x. So just to visualize what we're talking about, let's graph this. Now, remember y equals the square root of x has that shape. Now, if I replace the x with an x plus 7, that's just going to move that square root graph 7 units this way. So this is what our graph looks like. When x equals -7, we're taking the square root of 0. And when x equals -6, -6 plus 7 is 1. We have the square root of 1, which is 1. When x equals, let's say, -3, -3 plus 7 is 4. Square root of 4 is 2. And then when x equals 2, that's the point we're interested in, y equals the square root of 2 plus 7, or the square root of 9, which is 3. And so we have this graph, and that's our point of tangency, x equals 2, y equals 3. I'd like to sketch the tangent line approximation to the function at this point. We've got 1/6 times x plus 8/3. What does that mean? You know, rise 1 and run 6, right? So I go up to x equals, or I'm going up 1 to y equals 4, and then over here to x equals 8. So it goes through 4, or x equals 8, y equals 4. And if you go back this way, you should see a y-intercept that is just a little bit less than 3. It should be 1/3 less than 3. It's not perfect, but you get the idea. Look at that. Talk about almost indistinguishable. This is very, very close to the function. Now, in your homework on a couple of problems, you're asked to fill in a table of values. So they say complete this table. And the whole point of completing the table is for you to compare the values of y equals f of x and y equals t of x, that linear approximation to the function. If we're near x equals 2, so this is f of x. And then we've got t of x equals this. Oops, 3. We might want to approximate the function near x equals 2, that point of tangency. So maybe I'll go out to 1.99 and 1.9, 1.5. Maybe we'll go out to 2.01 and 2.1 and 2.5. Sorry guys, I had to step away from the computer for a second to get my calculator. Okay. But the whole idea is just to show you that the y values on the graph of the function and the y values on the tangent line are very similar. So I'll just use numerical approximations. I've got the square root of x plus 7, so 1.5, whoops, square root of 1.5 plus 7. I'm not getting exact answers, so I'll use decimal approximations. Let's round out to 3 decimal places. We get 2.195. And at x equals 1.5, let's see the y value, what the y value is on the tangent line. So I've got 1/6 times 1.5 plus 8 over 3. And that is approximately 2.96 repeating. It's actually an exact number. It's pretty good. Pretty good. And we're all the way out at 1.5. So we're a half of a unit away from that x equals x naught, which is 2 in our case. Okay, let's see what happens at 1.9. So I've got the square root of x, which is 1.9 plus 7. I get 2.983. And let's see what we get for the tangent line at 1.9. So I have 1 divided by 6 times 1.9 plus 8 over 3. 2.983. Okay, so they're already indistinguishable out to 3 decimal places. And then let's look at 1.99, square root of 1.99 plus 7. And I think I'll use more decimal places so I can try to find the difference between the two. I get 2.99833. And let's look at this over here. I've got 1 over 6 times 1.99 plus 8 over 3. 2.993 repeating, and 3 repeating is pretty much what I get over here, but there was I guess a 6th digit after the decimal place that would not agree with this one. And of course at x equals 2 we get square root of 9, which is 3. And then over here we should also get 3 because that tangent line passes through the point x equals 2, y equals 3. But let's check. What's 1/6 times 3? Or excuse me, 1/6 times 2? Hope you said 1/3. What's 1/3 plus 8/3? It's 9/3. What's 9/3? Well, it's the same as 3. So that's good. They agree there at that point. Now let's see what happens on the other side. Whoops, we have square root of 2.01 plus 7. I'm going to go a little bit faster now because I think you guys get the idea. I'll just say 6, 7 there. And then I'll have 1 over 6 times 2.01 plus 8 over 3, approximately 3.0016 repeating. You see, it's very similar. But now we're getting a little bit farther away from x equals 2. Let's go to 2.1. I've got the square root of 2.1 plus 7. So it's about 3.01662. And over here, we've got 1/6 times 2.1 plus 8 over 3. It's about 3.016 repeating. Very similar out to the 5th decimal place. That's where they differ. And then at 2.5, that's pretty far away from 2. It's half of a unit from 2. I expect a larger discrepancy between the tangent line and our original function. So here's our original function value. So look at the y values, guys. Look how similar they are, even at 0.5 units away from x naught. That y value is very similar to that y value out to the 3rd decimal place. So is this one. But the closer we get, the closer and closer we get to x equals 2, the more similar these guys become. The limit of this function as x approaches 2 is 3. And the limit of this function as x approaches 2 is 3. So using the tangent line as an approximation is a very good idea as long as you stay close to 2. And we can see it really just depends on how large an error you're comfortable with. That's very similar, but it's wrong out to the 3rd decimal place. Maybe you're not comfortable with that type of error. So it really just depends on you, how far away we can get from x equals 2 and still use the tangent line as an approximation. But again, the concept is if I zoom in and zoom in and zoom in, eventually that tangent line and the function are pretty similar, just like we see in this table. Okay. So we know what a differential is. It's just the derivative of the function times dx, or the derivative of the function times dx, and it's denoted by dy. And now we know how to find the tangent line approximation to the function. It's actually something we already knew how to do, but now we're interpreting it differently. And we're saying y equals mx plus b, where that is the tangent line of the function at x equals x naught, is a very good approximation to the function. So we'll call this the tangent line approximation of the function, or some books, some textbook authors call this the linearization of y equals f of x at x equals x naught. And again, why do we do that? Because that red line is very, very similar to the original function as long as we stay near x equals x naught. Okay, you might say, okay, what does that have to do with differentials? Now we're going to put those two pieces together. Now, when I use the tangent line to approximate my function, there's always a little bit of error involved. So maybe our function looks like this. Maybe this is x equals x naught. This is the y value that goes with it. We'll call that f of x naught. This is y equals f of x. And this is y, and that's x. Now, if I find the tangent line approximation to my function at x equals x naught, that's a line that's tangent to the curve there. It passes through x naught, y naught, where y naught is f of x naught. It has the same slope as the function. And we say as long as we stay close to x naught, pretty decent approximation. If x changes by a little bit, y also changes by a little bit. So let's say we're going from x naught to x naught plus delta x. This difference right here, that's the actual change in y. So when x is x naught, the y value is f of x naught. When x is x naught plus delta x, the y value over there is the function evaluated at x naught plus delta x. So that's f of x naught plus delta x here. That distance we're going to call the increment of y. That's delta y. This is the actual change in y as x changes from x naught to x naught plus delta x. Now, delta x in this application is often used interchangeably with dx. I know a lot of math people have a problem with it because dx is supposed to be a differential. It's supposed to be infinitely small, but we're not saying it in this case, in this context. We're saying in this context, delta x and dx are going to be the same thing. So delta x, we're going to say, is equal to dx, and some people really groan and it really bothers them for us to say that this finite change in x is equal to this infinitely small change in x. But whatever, we're just going to stick with this because that's what people do when they're studying differentials. This represents a small change in x. So as x changes by delta x units, and now we're using delta x and dx interchangeably. which is a problem for some people, and I get it. Then the increment of y is denoted by dy, or excuse me, delta y. And this is the actual change in y as x goes from x naught to x naught plus delta x or x naught plus dx. We're going to use the dx and delta x interchangeably. So this is just the final y value minus the initial y value. That's all it is. And the final y value is f of x naught plus delta x. The initial y value is f of x naught. And if you want, you could write it with the differential of x in there. And we're saying the differential of x and delta x are the same thing in this application. So this is the actual change in y. Now, if I'm using the tangent line as an approximation to the function, there's an expected change in y. If I'm using the tangent line as an approximation and x is going from here to here, the expected change in y using the tangent line as an approximation is this distance. It's the difference between this y value and then this y value. It's the y value on the tangent line. That is the differential of y, but be careful, it's not just the differential of y, the derivative times dx. It's the differential of y evaluated at x naught. Okay, so that's the tie-in. That's why this differential is somehow related to that tangent line approximation to the function. We interpret this differential of y evaluated at x naught as the expected change in x, or excuse me, the expected change in y using the tangent line as an approximation to the function. So let's write that down. I'm going to call this the differential of y evaluated at x naught. And what this represents is the expected change in y using the tangent line as an approximation to the function. So how do I find the expected change in y using the tangent line as an approximation to the function? Well, I compute the differential. It's giving me the slope at that point x naught, and then it's saying, well, take that slope and multiply by that change in x. That's how much y should change. Very important that you understand what this means. It's the expected change in y using the tangent line as an approximation. And this is using the tangent line as an approximation and assuming that x changes by delta x units. Say when x changes from x equals x naught to x equals x naught plus dx. And again, dx and delta x are used interchangeably in this discussion. This is a little change. I'm going to multiply by the slope. That's going to give us the change in y. Okay, so those are the definitions. Let's look at an example. This is actually very simple. This is one of the simplest standards in the course as far as computation is concerned. Sometimes students have trouble wrapping their mind around the ideas, but the computation is actually pretty easy. So let's say you're given y equals, let's say 8x minus x to the fourth. And we want to, let's say, compute change in y, the increment of y, and dy at x naught equals 1 when delta x and dx are equal to 0.01. Okay, and then we'll try to visualize this as well so that we can make sure we understand what's going on. Well, first I'm going to compute delta y. This is easy. It's just y final minus y initial. Now, the way you have to think about this, though, is the initial x value is x equals 1. That's where we're drawing our tangent line. And the final x value is x equals 1 plus 0.01. So I've got f of 1.01 minus f of 1. I can compute those two y values, and then I just subtract them. F of 1.01 is 8 times 1.01 minus 1.01 to the fourth. I have 8.08 minus 1.01 to the fourth. Approximately 7.039, let's say 4. Let's round out to 4 decimal places. Okay. And then we'll subtract f of 1, which is 8 times 1 minus 1 to the fourth. So 8 minus 1, which is 7. And then we subtract those, and we get approximately 0.0394. Okay, that's the actual change in y as x goes from x equals 1 to x equals 0.01. If I were on the graph, that's how much y would change. Okay, now we want to look at the expected change in y. Using the tangent line as an approximation, we want to compute dy. I'm saying exact, but it's like a numerical approximation actually. But normally we would interpret this right here is the exact change in y, and that's our numerical approximation of the exact change in y. So as x changes from 1 to 1.01, the y values go up by this much. The y's go from 7 to 7.0394 approximately. Okay, now we want the expected change in y using the tangent line as an approximation. In order to find the expected change in y, we compute the differential. That's the derivative times dx, and then we evaluate it at that point. So we're going to write out the steps over here. First, we want to compute the differential. Of y, and then we want to evaluate it at x naught. And x naught, remember, is x naught equals 1. So really, we just need the slope of the curve, and then we'll substitute in x equals 1. Okay, So I'll compute the derivative. Derivative of a constant times x is just my constant. The derivative of x to the fourth, well, first I bring my negative down, then I bring my 4 down, and multiply by x to the 1 less power, and then I evaluate that at 1. Y prime at 1 is the same as f prime at 1. And of course, I think we can all see that 8 minus 4 is going to give us 4. Okay, so the slope at this point is x equals 4, or excuse me, is m equals 4. So dy is 4 times dx at that point. And what that tells us is, as x changes by a little bit, the y values are going to change by 4 times that little bit if I'm on the tangent line. This time our delta x, or dx, which are being used interchangeably in this context, they're both equal to 0.01. So we compute the differential of y, we evaluate it at 1. And now we're going to substitute the value of dx, or delta x, that was given, which was 0.01. Okay, so this is the approximate change in y, using the tangent line as an approximation. As x changes from 1 to 0.01. Or excuse me, 1.01. Okay, so let's visualize this just a little bit. You can see that the computation is pretty easy. Delta y is just the change in y. Find the y at the new x value, the y at the old x value, and you subtract. This gives us the change in y, which is approximately 0.0394. Using the tangent line as an approximation, we thought that the y might change by 0.04. Turned out we were wrong, but only by 0.016 approximately. Not bad, depending on how accurate we want to be. But let's graph this. So I have y equals 8x minus x to the fourth. To graph it, I might want to factor it. This is x times the quantity 8 minus x cubed. And I can factor out this difference of cubes that factors this way. It's 2 minus x times 4 plus 2x plus x squared. Oops. This doesn't factor in the reals. So our function is equal to 0 when x equals 0 and x equals 2. If you're saying, why are you doing this? I'm doing this because I just want to visualize what the function looks like. And we found that at x equals 1, y is equal to 7. Ooh, this is going to be really bad unless everything is to scale. It's not going to be to scale, I'm sorry. Okay. So what we end up with is a function that looks roughly like this. Oh, actually, it has a slope of 4 right there. So it's going to keep going up for a while, and then eventually it has to come down at x equals 2 and then go down here. Okay, so that's actually x equals 1, y equals 7. What we've just computed is delta y is f of 1.01 minus f of 1. And we said that that was approximately 0.0394. So y is going to change by this many units as x goes from 1 to 1.01. And then we said, okay, well, what does our tangent line tell us? According to the tangent line, y should change by this much. Should be f prime of 1 times delta x, or f prime of 1 times 0.01, which is exactly 0.04. Saying the expected change in y and the actual change in y are very close. The actual change in y is just a little bit less than the expected change in y, using the tangent line as an approximation to the function. And of course, this isn't a great picture, but if I were graphing this on Desmos.com, or just graphing it with more points and to scale, it would be a little bit more accurate, but I think this visualizes the idea that we're going for. This is a numerical approximation of the exact change, and this is the expected change using the tangent line. Okay, let's review what we just did. It's actually really simple computation, but people can sometimes get lost. They forget what all of these symbols mean. So we're asked to compute delta y and dy. And remember, delta y is the actual change in y as x changes from this x value to this x value plus delta x. And if we look at our picture again, this is what we're doing. We're saying, okay, we're right here, we're on the curve, saying, well, the original y value, what's that? What's the new y value? Just subtract them. Just subtract them. And we're using delta x and dx interchangeably. Okay, so that's the idea. So what do? We find y final and y initial, and we subtract. And because it's a very long decimal, we approximate. Okay, that's the numerical approximation of the exact change in y as x goes from here to here. Just y final minus y initial. Now for the differential, this is giving you the expected change in y using the tangent line as an approximation. You compute the differential, but you plug in the x value where you started. That's where you're creating that tangent line. So we're plugging in the x value where we start, that point of tangency. Or in this picture down here, our point of tangency is x equals 1. Say, okay, well, what's the slope there? It turns out that the slope is 4. Then you multiply by the change in x. This says y goes up by 4 when x goes up by 1. And then we say, well, how does y change if x goes up by 0.01? Well, we just take the slope and we multiply by 0.01, and we get the approximate change in y using the tangent line as an approximation. So we compute the differential, plug in the x value, we get this, and then we multiply by the change in x. And we see that they're pretty similar, very similar. Okay, so that is our first part of the lesson on increments and differentials. Increment is the exact change in y. The differential of y evaluated at a point is the expected change in y using the tangent line as an approximation. We talked about the tangent line approximation to the function at x equals x naught. It's just the tangent line. It's nothing new. You've been doing this. We just call it something different, the linearization. And remember how that works. What are we going to do? You find the slope. You find a point on the line. If they give you the x value, you find the y value that goes with that x value, and then just go to point slope form. So you're just finding the tangent line. Nothing fancy. The fanciest part comes right here, where we say, okay, I'm not going to call this y anymore. I'm going to call this t of x to represent tangent line approximation to the function. What are we saying? We're saying this is approximately equal to the function as long as we stay close to x equals x naught. And then we visualize this way. And then we verified that idea that the tangent line and the original function are very similar by creating a table of values. And we're like, look at that. That y value and that y value are very similar all the way down. Okay. And then we started with this topic. We're computing differentials. This is the definition of a differential. Somebody asks you for the differential of y, and y is a single variable function. This is what they want. They just want the derivative times the differential of the independent variable. So if y is a function of x, we have the derivative times dx. If y is x cubed, we get 3x squared dx. Y is x to the fourth, 4x cubed dx. Y is sine of x, dy is cosine of x dx. You just take the derivative and you multiply by dx. It's very simple, and it's going to be very useful when we start talking about antiderivatives and u substitution and all of the techniques in the next chapter.